It's a great pleasure to introduce the next speaker, which is Giovanna Morigi from Saarbrücken. We'll talk about ion chains as quantum reservoirs. So please, Giovanna.
So thanks to the chairman for the introduction. Thanks to the organizer, to Chris Monroe and Peter Rabel, for the invitation, for the opportunity to be here. Welcome to my talk. I have a better news. This is not going to be a talk about molecular ions. I have a good news. This is going to be a theory talk. But since it's evening, we try to keep it a bit simple. And I give you now, we have discussed a lot in the latest 2 days about reservoir, open systems, and entangling two physical objects by means of an interaction which is not going to be coherent. So now I make a picture of a process, which is a process due to a reservoir and leads a system to a target state. And this is thermalization. It has been microscopically modeled 100 years ago by Einstein and later on by Chandrasekhar. And the idea is that you have a physical process. These physical processes are elastic collision. This elastic collision takes place between light particle and heavier particle. The light particles, say, form already a reservoir at a certain temperature. The heavy particle thermalizes, dumps to a thermal state at the temperature of the surrounding particles. Now, we know also that a reservoir induces not only thermalization, but can also establish correlations among physical objects. And one example, which is a textbook example, is superconductivity. There we know that correlations among electrons, according to the BCS theory, are established through a common reservoir, which are the bulk phonons. And the temperature of the bulk phonons controls whether we achieve this quantum phase transition to a superconducting state. So now I'm not going to talk about superconductivity, but I'm going to discuss ions as a bulk. I'm going to discuss when they act as a thermal reservoir, so that if you put a physical object interacting with it, it thermalizes because of the interaction with the phonons of the ions. And I discuss a situation in which the ions of a chain act over a reservoir that establish correlation at sufficiently low temperature between two objects, and these correlations are such that they are present at the stationary state of the asymptotics of the dynamics. I will then, depending on the time and on the phases I see, I will discuss a model of the spin boson model in which a single spin is coupled to an ion chain. We have had several examples of this. But I will analyze the situation in which the spin couples to the mode of the chain. This coupling induces the coherence. But if the chain is close to criticality, like to the second order phase transition linear to zigzag, we observe a recoherence. And this recoherence takes place at the frequency of the soft mode. And at the end, since I'm in a session about photons, I will talk about a peculiar steady state of photons and vibrations in which entanglement emerges because there is an interplay between Coulomb forces and mechanical forces induced by the light. So this is the system. This is a picture I took several years ago from the homepage of Michael Drevsen. There are 85 ions. And this is the model I'm going to consider. So it's an ion chain. Axial vibrations and transverse vibrations are decoupled. What you see here is the dynamics of the ions in the harmonic approximation. So here is the kinetic energy along the z direction, which is the axial direction here. Here is the potential induced by the electrodes of the linear Paul trap. And this is the interaction in the harmonic approximation. This KJL depends on the distance between the ions, scales as 1 over the distance to the cube, because we are expanding along about the equilibrium position. And it depends on the position. We don't have translational invariance. And for the transverse vibration, we have the same along x and y. I don't report the Hamiltonian in the y direction. And what you see here is the transverse potential, which depends on the mass of the ions. So we are taking a model made up of harmonic oscillator. So it's integrable. And the first thing, since there are a series of studies that are reported in the latest time, and that nobody expects thermalization in the system. But the point is the fact that if we look at time scale which are sufficiently so short, this is a model that have been analyzed in previous literature, which is the equivalent of the model equivalent. It gives rise to dynamics, right? The dynamics on the Chandrasekhar-Einstein model, in which one sees that the n minus n ions of the chain act as a reservoir for a single ion, dumping its state to a thermal state, thermalized at the temperature of the rest of the chain. Now, this is of course true as long as the time scale in which this thermalization takes place is faster than the time scale in which you realize that you have a finite size in your system. So it's the recurrence time, the Poincaré time in which you have, again, the recoherence. So how do you describe the dynamics of the single ion embedded in the chain? So you take, say, the motion, the x coordinate for this ion, eliminate the modes of the n minus n ions, and then you get an effective equation. So it's no more now unitary dynamics, no more coherent, but you have a damping term and you have a force, which is what you would call the Langevin force, plus additional terms that depend on the initial condition. And this damping kernel determines how your system has, experiences an effective, for instance, friction. And in particular, one important quantity in order to characterize how this bath acts on the system is to look at the Fourier transform of this damping kernel, and this is the so-called spectral density. And if you look how this behaves in terms of the modes of the ions, it actually depends on the spectrum, on the excitation spectrum of the chain in which this particle is embedded, and on the damping, on the strength of the coupling to each eigenmode. So now what I plot here is the excitation spectrum for an ion chain. What we see here are the axial mode. What we see here are the transverse mode. And where we have the axial mode, we have a more or less linear behavior with the frequency, so that we can say that if this is a spectral density which is relevant in the dynamics of our ion, then we have an ohmic reservoir which will give rise to thermalization. In particular, in this linear regime, this term here becomes a constant gamma times x point, giving rise to the typical friction we are used to in classical mechanics. So now, say we want to study the dynamics of an object embedded in this chain, and this could be, for instance, an impurity defect. Say a heavier mass ion which is crystallized within the chain. Now I show two and I put here, I highlight here the transverse vibration. Why do I do it? Because in a Paul trap, the frequency depends on the mass, and we can have that the oscillation, the transverse oscillation of these defects can be pretty close to an eigenmode, and they are separated, and they are shown here, and the dot around is in order to highlight this point. And this is a transverse excitation of the defects that is practically localized at the defect themselves. So now, say we want to study what is the dynamic of a single defect. What we would like to do, we would like to couple, say, the transverse vibration with the axial vibration. So we will have the coupling of an oscillator to an ohmic reservoir, and this can be done, for instance, by means of a laser that is a standing wave, and it's in the Landicki regime, and it can be treated in such a way that gives us rise to such a coupling between the transverse vibration of this ion and the axial vibration of this ion. And if we look at these dynamics and we observe what is the dynamics of this of the variance of this ion, then we observe a thermalization at the temperature of the rest of the chain. So this is as a variance as a function of the time, and then there is a revival time at which that is of the order of the size of the chain scaled by and the speed at which that you have to take into account in order to calculate the effective sound velocity you can associate to this chain, to the dispersion vibration of this relation of this chain. So now I take two defects. I motivated the fact that I would like to see whether this reservoir can establish correlation. I showed that in a regime of parameters that I've chosen, and I checked that this one single defect thermalizes. Now I couple two. What will happen? Now I assume that they couple by means of two lasers that couple each individual defect with the rest of the chain. So before I discuss the result, I make some preliminary considerations. So there are a series of works that looked at chain of oscillator and studied whether there is entanglement in the thermal state of this harmonic chain. And this is one of the first papers in which this was studied. This was a type of system that was considered, and in this system where the dynamics is Gaussian and the thermal state is also Gaussian state, you can look whether, for instance, you have entanglement by looking at the logarithmic negativity. This gives you a measure of whether you have entanglement and how much entanglement you have. It allows you also to quantify. So this is the logarithmic negativity as a function of group separation, because in this paper they analyzed entanglement between different groups of oscillator at different distances. And what they find, and they don't even plot it here, is that the curve for group size 1, so it's one single oscillator, is not visible because it is a single point. The log negativity between the oscillators turns out to be 0 whenever the separation is larger than 1. So the statement is that if you have a chain of oscillator and you put it in a thermal state, you look at whatever is the temperature, you find that there is no entanglement between two different oscillators. There are no correlations that can be characterized by entanglement. And there is also subsequent work by Janet Enders and Andreas Winter, in which they quantified also in a more sophisticated way these statements. Now, these statements are correct. The point is that I'm going to say is that they are based on systems, as they also observe in these papers, which have discrete translational invariance. So there is actually no peculiar properties that should single out the establishment of correlation between two particles. Say.
So why would one expect entanglement, like, since it's completely linear? I mean, like, it should just be the whole nodes, right?
That's true. That's the point. So now I say that instead we find it if we put two impurity defects. Okay. So you said what I was saying. Probably also in a much better way. So now I tell you that if I put two impurity defects in this chain and they are heavier, then I'm going to find entanglement.
What's telling you? Why does those entanglement?
Okay, I'm deaf.
What is telling you? Why should there not be entanglement?
It's just a bunch of normal nodes. I mean, like, well, if it's in a thermal state, it would just be a diagonal.
Okay, so now let's say the following. Since Alex asked you, let me go to this point, to this paper that I was not going to discuss, but just pass over. What did this author argued? So now you would say that the system is separable whenever you can use either the basis of the individual oscillator or the normal modes, and these two types of partition that would lead to the same dynamical description. But this is going to not be equivalent whenever you have a temperature which is below the freezing out temperature. Then you have the certain collective modes are frozen out, and only certain few collective modes are still thermally excited. And if these modes are thermally excited, then you expect that if you go back to the basis of the individual oscillator, you can find some quantum correlation among the oscillators themselves. A similar argumentation has been also brought up for a ferromagnetic system or antiferromagnetic system when you look at correlation among the individual spin forming the strongly correlated bulk. But the answer is there is no entanglement. And actually they find entanglement, but the entanglement is only between nearest neighbors, whatever is the temperature. And they find it also for adding some extra ingredients with respect to the paper of Adenauer and Plenier. So now I come back to these impurity defects. I observe that the symmetry by the translational, by the discrete translational symmetry is broken down. The discrete translational invariance is broken. But we have a symmetry per refraction. We don't have to have that these two defects have to be symmetric with respect to the center of the trap. But what is important is that they are sufficiently far away from the edges that if we have more or less an equidistant ions interposing them, then we can find a center for which we have there are some modes that are symmetric or antisymmetric by reflection. And if we have symmetry, then we have the coherence-free subspaces. So let us analyze the system in terms of these symmetries. We look at the center of mass and relative coordinate of the two defects coupled to the rest of the chain, here shown as a chain of oscillator. X caps log capital is for the defects, and X small is for the bulk ions. And what I show here, and I make a long story short, I show here the spectral density for these collective coordinates. So what I show here is a spectral density for plus, the symmetric, and minus, the antisymmetric, so say the relative motion, for a distance which is equal to 5. So 5 ions interposed between the two defects. And here for a distance which is equal to 10. And then you see that the behavior that one would usually assume to be regular for an ohmic reservoir is very different. One observes oscillation, and these oscillations have zeros that are alternated, where I have a zero of the spectral density for the center of mass, there is a maximum for relative motion, a local maximum, and vice versa. These zeros are corresponding to some modes of this chain for which the axial motion of the defect does not move. And they actually involve the transverse oscillation of the defect and the oscillation of the interposed ions. The rest is practically still. So what happens if you choose one of these zeros? Here what I show is the dynamics of the logarithmic negativity as a function of time, assuming that initially the two defects are, say, prepared in a separable state, in the ground state of their relative motion, or in a squeeze state, each. And so what one sees is that after a certain point, entanglement starts to increase. And the increase of entanglement depends on the initial squeezing, but you find it also for squeezing equal to 0. Actually, this behavior scales up with the number of ions in such a way that if you look at the characteristic frequency, that it scales with the number of ions according to the corresponding coupling strength. So you see that the coupling strength gives you the width of this band, and by scaling it up in not in a thermodynamic limit, then you get a different width of the gap as a function of the number of ions. And if you rescale it according to it, then you see that each curve for the logarithmic negativity overlap from n from 50 to 1,200 ions. Here they are shown chains from 800 to 1,200. For 50 ions, we get many oscillations that hide this behavior. Also, if we change the distance between the ions, we find a finite entanglement. And this entanglement does not scale exponentially with the distance, but it scales asymptotically linearly. What you see here is the logarithmic negativity as a function of the distance for different zeros that are chosen. So if you look at the spectral density, there is a number of zeros in which we choose the frequency of the oscillator. And at this zero, we evaluate the logarithmic negativity. Now, if we increase the distance, the number of zero increases, and we have different choices. And you can actually optimize the entanglement that you get by making the right choice of the dark mode. So now I want to argue why thermalization generates entanglement between the two impurities. And what I show here is a covariance matrix for the two impurities at t equal to 0. Now, these are two 2x2 matrices, which contains the correlations of each oscillator, of this impurity oscillator. And these are 2x2 matrices which are zeros, and show us that at t equal to 0, we don't have any correlations between the impurities. So now we argue in terms of symmetry and look at the dynamics in terms of relative motion and center of mass motion. And we can look at this matrix and this new basis, and then if we look in this new basis, we have correlation. But we did just change the basis, so we made the rotation, and this gave rise to off-diagonal elements. So this tells me that in the basis of the center of mass and relative motion of the two impurities, there are correlations, but then in the original basis, they are in a separable state. Now we let dynamics evolve. And we know that if we choose a 1, 0 of this spectral density, so the relative motion, say, will be decoupled, but the center of mass motion will be coupled and will be thermalized by the rest of the chain. So this thermalization gives rise to the damping of this off-diagonal term in the basis of center of mass and relative motion. And this is also a simulation which shows how the center of mass, here is the opposite, of the relative motion thermalizes and the center of mass remains practically untouched. Now, if we go to the original basis, now we have cross correlations. And these cross correlations can be such that they can correspond to entanglement if a series of conditions are fulfilled. One of the conditions is that, say, the center of mass is sufficiently squeezed, and this is a condition on the initial squeezing that we put on the two oscillator, and the relative motion is thermalized, so that the two quadrature, the two orthogonal quadrature, have a correlation which is such that is below the standard quantum limit. So it's a two-mode squeezing type of entanglement, the one that is created by the axial phonons between the two impurities. I talk about something different, but still it's decoherence, and it is decoherence induced by a quantum critical path, which is again the ion chain. And now I'm going to talk about a spin, not an oscillator, which is embedded inside of the chain. And the spin, say, is an internal transition of the ion between two states which are stable. And I'm taking the chain close to the linear zigzag instability. Actually, what I show here is a phase diagram that has been measured I think in 92 in the group of Herbert-Walter. And here you have the ion density and the potential depth. And here there is a series of points that shows you that for a certain range of parameters there is a streak, for other range of zigzag type of configuration, and then other crystalline structure. And I'm going here, close to this line. And I'm recalling the fact that this is a second order type of phase transition, the linear to a zigzag structure, and it has actually a soft mode, which is the zigzag mode of the linear chain, which drives the system, which brings the system into a new structure. This is an important point to keep in mind. And now I say why the chain acts as a reservoir for the rest of the spin, and this is a simple argument that has been brought in a very nice way by Wojciech-Zurek, but also I refer to a Fizerev letter of Englert in which he shows how entanglement gives rise to loss of coherence of a system that is coupled to a second one. So this is, say, here represented by a spin with spin up and spin down and a coherent superposition. We couple with an environment with several modes. Now, there are some dynamics which we are going to realize that give rise that the evolved states have a correlation between state of the environment and state of the spin. And if you look at the reduced density matrix of the spin, then the off-diagonal element depend on the overlap between the states of the environment. Now, if the state of the environment as a function of time become orthogonal, then this reduced density matrix becomes diagonal, and coherence has been lost. There has been an effective dephasing. Now, the system we consider, the setup we consider is an excitation of this spin by means of a mechanical effect. This mechanical effect is like a photon that is absorbed, brings the spin into a superposition of the ground state and the excited state, and the fact that several modes of the chain are excited give rise to an effect dephasing, which we are going to measure, and we are going to measure this orthogonal element by making a Ramsey pulse that should reverse the dynamics, but it doesn't manage because there are a series of phases that has been accumulated between the ground and the excited state. So say the initial state is the spin in the ground state and the chain in the vacuum. A pulse creates a superposition in which there is a ground state in 0 and the excited state in a coherent state. Now the evolution gives rise to a phase for this coherent state, and this phase of the coherent state is such that when one looks at the probability that the atom is in the ground state, for a single mode, one would have that this probability rises again up to 1 for a single oscillator, and at the periodicity of the single oscillator. But if you have several oscillators, which are the modes of the ion chain, and they are all incommensurate, the frequencies are all incommensurate, this is never going to happen, and you will observe, in average, a loss of coherence, a loss of visibility. So this is an entanglement between the spin and the mode of the chain, and if you look at the visibility closer, for instance, to the critical point, one observes a decay of this sort, and then oscillation about a value which is, say, 0.83 for the values that we chose here. And then there is a recurrence because the system is finite and one gets some recoherence. And if one looks at short elapsed time, then one sees that the behavior of this slope, salute, is such that it presents a cusp exactly at the critical value. Here we are on the side of the zigzag, here we are on the side of the linear, and this is exactly the value of the frequency for which one has a transition from linear to zigzag. Now, we bring this argument further, and we look at the quantum superposition of two intermal states in a spin-dependent potential. And now, if you see, I changed the framework of something that you had under different words. So say there is a spin-dependent potential for the ground and excited state. A superposition is created at the central ion between ground and excited state. So there is now a cut state in which all the ions are in the ground state, and say the chain is in the ground state of the zigzag. Or if the ion is in the excited state, then the chain feels another potential. The potential is, say, steeper, brings the chain to a stable state which is going to be linear, and the corresponding state which is going to be evolved is the excited state of the linear transition. So if one looks at the visibility of the Ramsey fringes in this case, one can, say, prepare the potential so that when the atom is excited, then we have another zigzag. So we have a zigzag with a shallower in the ground state and with a bit steeper potential in the excited state. We can choose the parameter so the ground state is in the zigzag and the excited state is in the linear, or we can choose the parameter so that ground state and excited state are in a linear or in a steeper linear. And this is the behavior of the visibility for the three cases I mentioned. So it decays fast from a transition from zigzag to zigzag, and one observes some sort of revivals, but these revivals are getting more and more dispersed. From zigzag to linear, there are revivals, but these revivals are always going to be at the same frequency. And from linear to linear, one observes oscillation, but between the visibility is very close to 1. Now, what you see here is a contour plot of this periodic revival as a function of a parameter that tells us where we are. Till this point, this parameter tells me that I'm making a transition from a zigzag to a zigzag. From this point to this point, the transition. From this point to this point, the transition is from zigzag to linear. And here we are on the side of the linear. So these white lines tells you where the revival occurs, and then you see that the time of this revival is going to diverge at the point of the transition from linear to zigzag, exactly where the critical point is met. And if one look at the frequency, at the frequency or at the spectrum of this signal, here the visibility is always close to 1, so I don't discuss it. And now I focus on this part, and if I look at the Fourier transform of this signal, then you see that you get a characteristic frequency at which you get this revival. And this characteristic frequency is the frequency of the soft mode. And actually, this Fourier transform gives you the spectrum of the transfer excitation of the zigzag chain. So you observe revivals. There is recoherence, and this recoherence occurs because the linear and the zigzag structure re-overlap again at the frequency of the soft mode, and this gives rise to an effective reappearance of the Ramsey signal. So 5 minutes. I will be very fast, and just to connect to the talk of Ladan. I'm going now to change a completely system and discuss about other kind of steady states. The steady state occur because of other interactions. These interactions are due to placing ions inside of a high finesse optical resonator. This high finesse optical resonator is driven by the side and interacts with the atoms. And this interaction by the side gives rise to an effective potential, and this effective potential is a detuning, and a frequency shift, which depends on the position of all the ions. And here A and A daga indicate the annihilation and creation of a photon of the cavity mode. And if I look at this effective potential, effective shift, then we see that for the specific mode function that we choose is equal to the cosinus square of k times the wave number times the position of the ion along x. And x is here this coordinate. Now, what does this tell you? It tells you that, for instance, if you pump a photon inside of the cavity and you have a certain configuration, you can be resonant if the ions are placed in such a way so that this effective detuning, which is the difference between the detuning of the pump from the naked frequency and this effective potential due to the ions, goes to 0. So it tells you that the system has a certain preference to choose configuration of the ion which minimizes this potential. On the other hand, there is on top also the Coulomb interaction, which is in general stronger and tends to bring the ions to certain configuration according to the phase diagram that I repeat to show here. And now, again, I choose a situation in which we are close to the linear zigzag instability, but we are not at the linear zigzag instability. So, in absence of the resonator, the ions form a linear chain. Now, looking at the effective potential for the soft mode, the effect of this optical resonator is to add an additional term which is nonlinear and scales with the cooperativity. And indeed, if you look, and it scales also with the intensity of this pump that drives the cavity, so on the number of photons that are inside of the cavity. So if you increase this number of photons, what you see is that you can drive the effective potential of the soft mode from a single minimum to 3 minima and then to 2 minima again. What does it mean? It means that in this situation, the chain is linear. In this situation, it is more energetically convenient for the cavity plus ion system to choose a zigzag configuration, but still the chain is the linear chain is a local minimum. And then for larger pumps, the energetically favorable configuration is a zigzag. So either the ions form a zig or a zag, if you look at this as a Landau potential. And the corresponding signal at the cavity output is a hysteresis of bistability. To make a long story short, if you look at vibrations, fluctuation about this region of bistability, and so you say you choose the zigzag, and you look at vibration of fluctuations of the ion from the equilibrium position about this point, and fluctuation of the field among this point, then one finds that these are entangled. What I show here is the logarithm negativity as a function of the pump power, so P is eta squared. And this logarithm negativity is taken from an interval of parameter when one has the bistable behavior when the ions form this effective zigzag. And this is understood in terms of the emergence of a structure which is put together both by Coulomb forces and mechanical forces, and so that fluctuations about the equilibrium position present a strong quantum correlation between vibration and photons. And indeed, this is visible, these features are visible in the spectrum of the cavity output, giving rise to broadening of the lines about the eigenmodes of the zigzag chain. So I give a short summary here. I discussed ion chains as tunable quantum reservoir, and in particular, I showed that there are memory effects. We can switch actually from a Markovian to a non-Markovian reservoir by, for instance, adding this second laser which coupled the second defect to the rest of the chain. And then we see that due to symmetries and thermodynamic properties of the chain, we can identify parameter regime for which we find, for instance, entanglement between the two impurity defects. I discussed also shortly novel structure emerging from the interplay of optical and Coulomb forces, and in which we get entanglement between photons and phonons, and this entanglement is also an entanglement that can be used as a resource because the light that comes out from the cavity field is going to be entangled with the vibration inside of the cavity. And I am just giving a series of possible outlook. I just go faster through thanking the people who worked at several stages in this work, and in particular I mentioned Thomas Fogarty, Bruno Tachetani, André Cagliari, Cecilia Cormin, who's now in Ulm, and Jens Baltrusch, who made all the calculations for the Ramsey interferometer, and I thank you for your attention.
Giovanna, so, questions? Yeah.
Really nice. Just as kind of a slightly related, it's an open question in plasma physics and a very big question of what heat transport looks like between two component plasmas. As soon as you're really close to that system, so two component being different masses.
Yeah.
Do you think that there's any chance of scaling up what you're doing to, I don't know, what's the biggest ion number you have, and could you go quite a bit beyond that or start to chip away at that?
So far we have focused on ion chains, and trying to be close to experiment, we always try to limit the number of ions to 50, and this is the reason why I showed no more than that, for which I showed this first graph. Now, if you increase the number of ions and you go to, say, 1,000 or 2,000, then these effects are going to be even more evident, and the presence of entanglement asymptotics is going to be measurable. But for the discussion that I made here, then this would mean to have 1,000 ions on a line. Yeah. We have analyzed, we are analyzing what would happen if you have, say, a body-centered cubic type of structure, and you have so something like 10 to the 6 ions. In this case, it would make sense. Now, the point that is a bit more difficult is to identify what are the important configurations for which you can identify this defects mode. Because once you have it, then you can rewrite the spectral density, and you know how the dynamics is going to be. And you can simplify the problems and also analyze it analytically. Otherwise, one would be looking at the full numerical calculation. But so let's say that once this symmetry is present, I'm sure that it's possible to observe this effect. Yeah.
If I scale in the same problem the number of impurity ions,
yeah,
will there be one mode that will be strongly entangled, more strongly,
yeah,
with the number of ions, or will there be several modes?
Yeah.
That
Okay.
will be weakly entangled?
So let's. I rephrase it, so that in order to see whether I understand the question. So now, when I say, for instance, that I set the oscillator at this frequency, so that it is at the 0 of the spectral density, this mode is going to be decoupled. So it's like a dark mode. So the two ions are oscillating and the external one are. So this mode is going to be, say, squeezed, and the orthogonal quadrature is going to be thermalized. And so now, whenever I do this, I identify just one single mode. If I scale up the number of modes, and I'm within the thermodynamic limit, so that this value here will not change. So, sorry, if I scale up the distance, not the number of modes. And if I take a larger distance and this remains constant, then I get that the 0 becomes more and more dense. So they get closer to each other. And the requirement that I can just meet one single zero and decouple that one is going to be more difficult to fulfill. In that case, then I think I'm going to deteriorate the entanglement, because the participation of the ions. So I'm going practically to get statistical mixture of the two modes, and this and I will so the entanglement that I get depend on the zero, because the participation of the defect ion on that mode changes depending on the frequency. And whenever you do this, practically you get, and when you trace out the rest of the ion, you get out a statistical probability of finding one configuration or the other, and this deteriorates entanglement. But I have to say I didn't check it to that detail. It's more a simple calculation than one I performed. So
maybe I have a question. I mean, respect to this also. I mean, if you think about making an experimental realization of this, I mean, what is the kind of limitations in terms of excitation you can have? I mean, you probably make some assumption in your derivation of this model. I mean, so so do you have to be in a Lambdic regime still or something, or what is the?
So then I would say that the Lambdic regime is not going to be the main. So the Lambdic regime here, it has been used just to model this type of interaction. Where is it? So that we can write that we have like a harmonic oscillator. But if further terms are present, this is not going to be that relevant for the dynamics. What is important that it is a local excitation. What is more delicate is the temperature of the rest of the chain. And this has, and what is important is what is the temperature of the rest of the chain in terms of, so what is the number of excitation of the chain at the frequency of the oscillator. Now these are transverse, radial excitations, and they can be sufficiently large so that the rest of the chain has axial modes which are hot but still is cold with respect to that frequency. And if you set it as a value, so we found, we have pushed it up to 100 microkelvin and still found entanglement.
Other questions? Right, then thank you, Anna, again.